Hello everyone, this is Ricardo Tellez from the Construct, and here today I'm going to present you the concept of the Rosject as a way for reproducing robotics research results. So what is the problem that we try to solve? Well, it's the problem that we have been suffering for forever, I think, in robotics, is to prevent the re-implementation of robotics experiments. As you can see on this cartoon, very funny cartoon made by PhD Comics. So we'll also add some value to this, is that to keep the experiment that we are going to create for robotics to keep working for years. Not just for right now to create the paper that we have to present, the video we have to present, and then never works again because we are changing some things in our system. Then we don't pay attention to our current experiment, and then it becomes obsolete. Also, we would like to allow others to reproduce our results, so they can check that what we are claiming in our paper, then this is real, this is true. And also the purpose is to allow others to continue from our work. So imagine that you are on a lab and then you have some students that are working there, then you prepare your results, you get the PhD, you get the papers published, but then this work has to be continued by somebody else, as this is represented here on the cartoon. So they have usually many times they have to start re-implementing everything again. So by using this concept that we want to introduce here, we'll allow other people to start from our place, from our point, without having to start from the very beginning. And finally, the thing that we would like to introduce is a simple and easy way to share those experiments, those robotics experiments. So you don't have to copy those files or put in a Git, then afterward doesn't compile afterwards, then you have to install many libraries. No, just a simple way, maybe with a single link, web link, everybody will have access to everything. So the main motto, the main idea behind this presentation is that if we have an experiment in robotics that has worked for you, then it has to work for anybody else around the world, and in the exact same way, independently of which kind of computer the user, the person that tries to reproduce your result is using, Linux, Mac, Windows, whatever, and also independently of the configuration. I mean, Windows 10, Linux, Ubuntu 18, so that is independent. That's what we try to achieve here. And for that, we have divided the process into 3 steps. The first one, in order to achieve this goal, is to select a common testing ground. And for that, we have decided to use simulations, robot simulations, and those simulations have to be on the cloud. Why do we have to do this? Well, because using simulations, we remove the dependency of having to have the robot. So the people who are going to reproduce your results, they don't have to have the robot that you have. Because if you have a simulation, then you can include that inside your elements that you are going to create in order to reproduce the results. So you are going to provide this simulation already to the people who has to reproduce your results. And that's preventing to having to have the real robot on this. And then also by being in the cloud, then it's a way that we can achieve to remove the dependency on the user's computer. So if the creator of the experiment is using a Mac with this type of operating system and this configuration, then the results can be reproduced by somebody else that has a Windows machine with a lower CPU and I don't know, an older version of the operating system. So the second point is that we have to select a common programming framework for the robots. Yes, because otherwise it's too broad, the way the system that we have to support that provide this reproducibility. And then in that case, we have selected for our proposal is to use the robot operating system that you already know, that is ROS, of course. And why? The reasons why is first because it's becoming the standards in robotics, as you know, because you are hearing about that everywhere. everywhere, then there is a lot of code and simulations already available. So we can reuse that for our own experiments and not start from zero. And also it has a lot of chances to work in modern robots. So many of the modern robots, they already run on ROS. So we have more chances if we create experiments, if we do some code for robots, then it's more likely if we use ROS, because many robots that we can buy, they already provide ROS. Then the third point is to decide a proper structure for all the files that are going to compose this experiment. So as we are talking about simulations, for example, so we need to create the simulations. Also, we are going to talk about the files that are composed for the actual ROS code of our algorithms for the testing, maybe data sets, etc., all the files. For that, we propose what we call a ROSject. The ROSject is the contraction of a ROS project, and it's just a set of files including the experiment code, the simulation of the robot, the documentation also, and the required data sets that we are going to use there. So how does it look, the ROSject structure? Well, ROSject, it's meant to be executed on the cloud. So that's why we have a structure in some way that is useful for us to be executed on the cloud. Don't worry, because you can also execute it in local, but at that point we cannot certify that it's going to work in the same way as in the cloud, of course, because the computers where you put in local, then the configurations are different. But you have the chance, if you have the knowledge about how to recompile, install extra dependencies or whatever. Then the ROSject is defined for a fixed version of the Ubuntu system, a fixed version of ROS, and a fixed version of Gazebo. And that is necessary in order to be able to provide the same results. If we generate the results with a certain Ubuntu version or ROS version or Gazebo version, then it may happen that if we change any of those, the results will be different. So the ROSject is defined for that fixed structure. And the files of the ROSject are structured in the following workspaces. First, we have here the ROSject, and then we create what we call a Catkin workspace. That is the one that is going to contain all the material for the ROS code. So this is about our experiments, our algorithms that will run inside the robot or inside the simulated robot. But that's a code that should be running on the real robot. So we put it on the Catkin workspace. Then we have a simulation workspace. Is about all the files related to the simulation only. So we are separating here the ROS code of the algorithms from the simulation in two different workspaces. Then we have another workspace that is the notebook workspace that contains all related about the documentation that we are going to create for this specific ROSject, that is explaining how to reproduce the results, the steps that are required and the expected results. And then finally we have another workspace that is the one that is going to contain the data sets in case that we need it, of course. In case that you are needed to, for example, a data set for training your robot with some data, then you can put it there. Also for generating data sets, in case that your project, your ROSject, is related to generation of data sets for later training or whatever. Then here let me show you a list of the ROSject advantages if we use this kind of structure. First is that you don't need to install anything. So if you provide a ROSject to somebody else, then they will not need to do any setup in order to execute it. No compilation, no download, not installing libraries, no making work with your own computer. It's going to work by default without requiring any installation on the computer of the other guy. Then they can be reproduced. Because of that, they can be reproduced on any type of computer. So forget about Windows, you need to have Linux, you need to have Mac, whatever. No, just doesn't matter. And also the same reproduction conditions will be the same for everybody. So why? Because it's using the cloud, and then in the cloud the instances, the system that is reproducing this specific Rosject is going to be always set up, as I explained on the previous slide. Then another feature very important is that the Rosject can be shared, create a copy with just using a link, a web link. So when you share your Rosject with somebody else, you just provide a link to him. And then by clicking on that link, an automatic copy will be generated of the whole Rosject to the other person. And of course, the Rosject can work forever, even if it is for an old ROS version or Ubuntu or Gazebo. So what I mean forever, I mean for a proper certain amount of years, not forever ever, because forever is very long, but you understand what I mean. So it's not going to be close, not working anymore in 2 years from now. So it's going to be for a very long number of years. Then another option is that you have with the Rosject is that you can download the actual Rosject, because they are just files in standard ROS workspaces. So you can download it to local machines and use it in your local machine if you are willing to put the effort of doing that, because then in that case you will have to compile, see if there is any difference between the libraries that were used on the cloud and related to the ones that you have in your local machine. Also, you will have to have a Linux machine in your computer. So if you are willing to do the effort, then that is possible. So the code is not locked in the cloud, but can be executed and downloaded and observed and inspect in the local machine. Finally, Rosjects are Git synchronized. So what that means is that if you have a Rosject that you are modifying, you have, for example, share your Rosject with somebody else, and your Rosject was contained code that was from your Git, then you can update your Git, and by updating your Git from the Rosject itself, then the other Rosject that have copied, the other people that have copied your Rosject, they can receive that update if they want. They can do a Git pull and then receive all your changes. Remember that when you create a copy to somebody else, it's a copy, it's an independent copy. So that copy that the person who receives your web link, it's an independent copy, so whatever you do in your original one will not be transferred to the other one, to the copy one, and the other way around also. So if the copy, any modification to the copied Rosject will not be transferred to the original one. They are independent. So a way of avoiding this independency is by using Git actually inside the Rosject. So all the code that you put inside the Rosject is a Git clone. So you can then update, pull, push, etc. Finally, we can take advantages of the cloud without having to do any extra step, because you are executing everything in the cloud. So if the cloud provides more functionality, faster computers, other services, you can access them directly from there, because everything is executed on the cloud already. So you can take action on those new functionalities of the cloud if you want. If not, without cloud extras, that's okay. So it will work the same way. So here, let me introduce you an implementation of this system. It's inside what we call the ROS Development Studio. That's an online tool that it's on the cloud. We have developed at the construct, and you can see here a link to itself. So if you click on the link, then you will be put inside the ROS Development Studio. And then here, okay, so I was preparing some stuff for the presentation. So here, what we have, let me go to this link here inside the ROS Development Studio. So what we have is a lot of, it's a lot of Rosjects that we have created. In that case, some of them are for my live classes, or some of them are from experiments. Many Rosjects that we have here, and this platform is already online. You can access to it and get Rosjects already available. So you can search for all the public Rosjects that are already here, and you can see that there are more than 4,000 already Rosjects available. And here there is a link for more for the complete list. It's 4,200 public Rosjects with different subjects. You can search for terms and different configurations because it accepts different types of, as I mentioned, of Linux, ROS and Gazebo versions, even ROS 2 versions. For example, if we select all the Rosjects that are available for ROS Crystal, then we get all those that they are working already with ROS 2. Okay, so I don't know what is this picture here, very funny picture, that is cool. I don't know who has done it. Okay, so here is the user. You can observe the user on Very Technologies and open it, the Rosject, and see what they have included there. So that is up to you. But the platform is already there, as I mentioned, and you can start using this concept of Rosject that I have mentioned. And so the ROS Development Studio allows you to share the Rosject with a link and even also to connect to the real robot. So this implementation here even includes an option to connect to a real robot once you have your system working with a simulation. So you can test on the real robot directly from the cloud platform. And at present, we are supporting ROS 1 Rosjects with Kinetic and Gazebo 7 or Melodic and Gazebo 9. And also ROS 2 Rosjects with ROS 2 Crystal. So during the month of July, we are going to add ROS 2, what's the name? Okay, I forgot about the D version of ROS 2. So, okay, so how do we use this for reproducing results of papers? So we took an example in order to show you how is the functionality that you have to use, how you can do it, to how you can reproduce robotics results. So what we did is to take one paper that we found very, very interesting that is called Domain Randomization for Deep Neural Networks, from simulation to the real world. And it's a paper from 2017 from many people from OpenAI. So what we wanted is to reproduce their results. Basically, their paper is about training a robot inside a simulation to distinguish where the spam object is on a table with many different distractors around. And then once the robot is able to distinguish where the spam object is on the table using the simulation, then transfer that learning into the real robot and see if this robot can also distinguish where the spam is in a real environment, not only on the simulation. So we try to do this reproduce these results by using Rosjects, and then let me tell you the limitations that we have on this problem. First, on the original paper, there was no ROS code available because they didn't use ROS for this. So we needed to create everything from zero. Then also, there was no simulation provided. I mean, no Gazebo simulation provided because the guys from this paper, they used another simulator. It's called Mujoko, and there was no simulation for Gazebo version. And also there were some very vague instructions in some of the points, so we have to figure out what to do in some of the points and see if that will lead to reproduce the results. So what did we do at the beginning? The first thing that we did is to create the fetch simulation, because that's the place where we are going to do the training, of the robot. And here it is. You can see it's a simulation where we have a fetch robot, then a table, and then many objects around to distract the visual system of the robot, and also the spam object that is going to be shown here in the close. So right now in a few slides. Then we implemented the domain randomization system as a Gazebo plugin. This is the main point of the paper. It's that by using domain randomization, you can create a robust visual system in simulation and then transfer to the real robot. And that is the plugin that we implemented here. Basically consists of showing and modifying the situation where the robot has to recognize the spam object with different light conditions, color condition, different distractors. In this case, you can see one single distractor, but in the other later, you can see that it has many distractors around. So that's what we did to implement this domain randomization plugin. Then we use all this, the simulation and the domain randomization plugin, to generate the training dataset process. So that dataset is the one that would be used later on a future step to train the visual system. And as you can see here, you can see that this training system consists of first launching all the objects in a random way with different lighting conditions, then taking a capture from the image visual system, from the cameras that you can see on the right. And that was one of the sets of the data, one of the training data that we generated for the training data set completely. Then we use, with this training data set, we train a deep Q neural network with that data set using Keras. And then we tested the trained neural network with this simulation and checked that it was actually working and taking the spam object from all the distractors. And here you can see some of the results. So it's launched in different situations with different distractors, different light conditions, and then it's detecting where it is. Finally, we created a notebook with the full documentation that explains how to reproduce those results. So it includes everything from how to create the data set, how to use the domain randomization system plugin, etc., etc. It contains everything step by step with images, code, etc., as you can see, and how to reproduce the once you have the training trained neural network, how to use it for recognition. So the Rosject that we created for that contained the fetch simulation, the domain randomization code, the dataset generation code, so the code that generates the dataset. We also have included the dataset. Actually, it's more than 7 gigabytes, but the one that we have generated, even if we explain how to generate your own dataset, and we include the dataset generation code, we already provided the one that we use just in case that you want to reproduce the exact results as we had, and also in order to prevent you from doing the dataset, the generation of the dataset, because it takes a long time. Then we also provide the deep learning training code, how to train your neural network, and how to reproduce the code using the training network. And finally, we include, of course, the documentation. And here is the link. So how do I share this Rosject with all this information with you? How do I do? By using this link here. If you type this link in your web browser, you are going to get all this stuff here, and you are going to be able to get the same results as we have. So that's the amazing power. So if you click on here, well, you cannot click, but you can copy this. It's a very simple link. So let me show you how it works. So I click on here, then it's going to open on the ROS Development Studio, and then it's going to show me that it has been copied successfully. Okay, so here it is, my copy. Sorry, I have two because I was testing before doing the presentation, so you can see that it is here, my previous, but this is the last one. And about how to launch it, in order to launch it, you only need to click here on more, and then select Open Rosject. In my case, I'm going to select hardware, Pro 1 hardware, because I want to execute with more computer power. And in your case, it will be basic. It works with basic. We have developed everything using basic, so it's okay. So once you click on open, then it will load the project, get the files of the project, take into account that this is a heavy Rosject because it contains a lot of data. And then you will see that it will open. The first thing that it opens directly is the notebook containing the instructions, so you don't get lost. So let's see. Then the first thing that it loads is the notebook. Here it is. And here is the notebook that we have created. It says about duplicating robotics results, domain randomization. And this is a Rosject about this paper that you can get here. We have constructed ourselves, Miguel Angel and myself, and more information about this, the tools that we have used, etc. And then how to start a quick demo. So you have to go to the simulation, select the launch file, select this main const orientation launch. So go to simulations, here select the launch file that says fetch domain randomization. It's called main const orientation. Main const orientation, here it is. I select this and then I launch it. So now it's going to launch the simulation directly. And I don't know what is going to, yeah, so here is how we select that. And then we should get this simulation loaded and ready to start. Let me put it this bigger so we can select here. Then finally we have to open a web shell and then activate the neural network, so the system will start applying the neural network that has learned. So here we have the simulation with some of the objects already there. The robot is getting ready, and then in the meantime let me launch the command that it says. So I need to open a web shell here and then do those commands here. So it says I can copy and paste actually. So let me copy and paste everything. So it's going to recompile everything to start from zero. And I open a second web shell. Yes, so let me copy paste. So it's going to recompile everything, and once it's compiled, let me put it here and organize some way. So we can see everything. Then it will start using the neural network for that. So is the training. This is starting the training. Okay, so here it is. It is compiling and doing everything that needs to be done here. I don't know how long it's going to take for this to compile. I would like to show you about the results when everything is running. So let's wait a little bit for this. It's almost there. In the meantime, I can show you that this is a quick start. So this is the quick demo. So you can start the simulation and evaluate the performance. So it's using the already created neural network. And yeah, it shows, it also indicates how to open the RBase, so you can see the results in the RBase and get this kind of setup. So we are going to see how the objects are launched on the table, and then how the robot is detecting the location of the object, and then how it afterwards it tries to grasp it. And then after that we have the complete documentation about how did we achieve that. So you are going to be guided into all the steps that I have already described: how to generate the random material, the random data set, how to train, then how to apply, etc., etc. As you can see here, contains all many details and the results. So you must be able to reproduce the results, the exact same results. And this is about to finish. So here it is, and then I'm ready to launch the demo. So it should start now. We should see here how it starts everything and launching the objects there in a random position. Let's see how it starts. And also we can even do it like this, put it bigger. Okay, it's initializing the models. And let's see when it starts launching. Here it goes. So it launches all the objects with different lining conditions and different positions, different colors. And there it is. So we can see the results on the RBase. You can go to tools here, to graphical tools, and see the RBase that should be open, and that we should see the results. So here the robot has already detected where it is, and then it's going there. And here you can see all the extra data related to the detection. Okay, yeah, so in this case is colliding against the object. That's not, I mean, that's not a purpose of the paper, to avoid colliding with other objects. The purpose is to try to grasp it where it is actually the object, and that's achieved completely. Okay, so you can follow the instructions here about how to do it. Okay, so let's go back to the presentation. So here let me show you a few more ROSjects that we have created. We have created many of them, but here some that are interesting. This is one for training a carport with reinforcement learning. You can get the ROSject here in this link. Or we have another one here, for example, with the Talos humanoid robot. That's a human-sized humanoid robot by PAL Robotics, and then you can get this simulation including walking behaviors for the robot, and then you can use it for your own humanoid research. Also, we are using Rosject for providing live classes every Tuesday. Every Tuesday in our channel, we are using the Rosject to provide a class, a material class for our students. It's a free class that anybody can attend on YouTube. And at the beginning of the class, we provide a Rosject link that contains the material we have prepared for the class of the day. The class, they depend on the day. It's completely random what we are teaching there, and it's about the ROS subject or robotics using ROS. And then also we have some interesting ROSjects, like for example this one of the Curiosity Mars rover that you can get it here. So you can get the ROSject and have this simulation already working with all the joints and controllers, etc. Other applications that we have been using ROSjects. So, for example, for benchmarking of different solutions. Actually, we haven't used this yet, but this is something that you can use for example, reproducing results and comparing results in different areas of robotics to evaluate a robotics contest. So we have some contests in our pool at present that we are preparing, where the contestants will have to provide a ROSject, and they will be able to execute in the contest in the same conditions that they are having actually now that they are preparing the contest, because they are using the cloud. Also, as exam for students, I have used this a lot while I'm doing some ROS classes at the University of La Salle, and I provide an exam as a ROSject, and then also afterwards I can reproduce these results of the students. And of course, as I mentioned about the live classes, here you have the link in case that you are interested. Is every Tuesday on our YouTube channel at 6 CET time. And many others. Limitations. In order to finish, let me show you the limitations that we have of our system at present. It's only applicable to full robotic solutions. I mean, if you are trying to make a controller for a type of joint, that it's only the communication between the electronics and the controller, and so all that is not possible to be done yet at present in the ROSject. It's for a complete robot. Even if it's a very simple robot with a 2 motors pan and tilt camera, or a 2-wheel robot, for example, it's only available for those type of robots. Also, we don't have real-time control at present, but maybe it's something that is going to change if we work deeper with ROS 2. Then other frameworks, other robotic frameworks are not supported. If you are programming in other frameworks that are not ROS, then this is not supported. And at present is only working with simulations. That's one of the requirements that we did at the beginning, but we are working on this. Also, as I mentioned, we are providing a connection to the real robot. This is something, let me show you here. It's something that we have to show. It's here. Let me show you. And I have some problems to show you, but well. And then, so I cannot show you now, but don't worry, as the concept is that we are going to work on this, that only works with simulation, by implementing better simulations and applying the concept of digital twin. into our system, and also implementing better transfer to the real robot. As you have seen in the domain randomization, you can train in the simulation and then transfer to the real robot. This is a subject that needs to be improved in the current systems for simulations, and then we are working on that to make this better. And basically that's all. So here is my name, my contact details. In case you have any question or doubt, don't hesitate to contact me and let me know your thoughts, let me know your requirements, let me know if you want to use this system. Remember that it's for free. It's so it has a layer that is for free, and that's very useful. It contains a lot of features. And have a look and let me know your opinion. So I'll be happy to be here and answer your questions. Thank you.